I thought I'll fix the script meanwhile, but there was another mistake, and I saw it pretty lately. So the good solution here is just to downgrade it to the proper version of NetworkX, and it seems that now everything is working, but we need to do the same thing at the previous steps here. Yeah, so you need not just to install NetworkX, but to install it with the exact version. And in this case, everything should be okay. Okay, because here you see it, so there are some other dependency collisions that happens from time to time when you're working with Python. And yeah, sorry, shame on me. And if we restart the runtime, then everything should work properly. Yeah. So BEMS, this should be put upper, yeah, like this. So I will run it again, and I should return the matrix back instead of array, just to make things work good. Sparse. Where's another match here? Yeah, here it is. So I'm just undoing the changes that I made, and now everything should work fine. So yeah, he's reading the data set, and we need to run it once again. Just a small spoiler, if we're, oh my God. You know, this is the first time I get this picture. It looks like we have the nodes and everything is okay with them, but the edges are kind of shifted at the fixed size, because this branch should be here. Yeah, and that's very funny. That's the first time I'm seeing this picture. In fact, inside NetworkX, you can control the coordinates of the nodes, edges, labels, wherever you want. Yeah, so you can compute coordinates once, and then your coordinates will be fixed forever. So you have a lot of control in doing this. But if you are not parameterizing this argument, the coordinates one, then you're getting just the spring layout using the Flirtenheim-Reinhold algorithm, and so everything should be okay by default. But in this case, so we have a very funny mistake. I guess we should just run it again to fix it, but it takes some time, so I will not do it right now. Делать я этого, конечно, не буду. So just a small talk about node2vec. Yeah, so here we're training our node representations separately with our final goal. So we're just training some information about nodes without any idea about the task that we're going to do. Yeah, so I'm reading the comments, and yeah, so in fact, the fixes are pretty simple. Talking about the new version, it's just the renaming of several functions, but it takes more time than I thought, so it's easier just to downgrade to the proper NetworkX model. But the good story is that I have stored results here, and let's just dive into the general idea here. So we have learned the embeddings using this node2vec algorithm with one iteration on 8 workers, and we have just talked about the parameters. Yeah. And then we need to compute the probability of an edge, yeah? And our general idea is that so to do this, we need an edge embedding and some kind of classifier that will say if this edge is more or less probable, yeah, if this edge is probable or not. And in our case, since our node embedding is static and doesn't consider the practical task that we're solving, where we will do just the multiplication of two node embeddings, and that's all. Yeah, so it's extremely simple and primitive. And so our assumption is that if our embeddings are pretty close to each other, then our edge embedding will be pretty large, and that will maximize the probability for this embedding to exist. Yeah, so we're solving a pretty simple logistic regression function, and you can use any other function you like. You can add a neural network based on the embedding training processes. You can use random forest and some boosting here, but so logistic regression is something you can always use, and it's simple and understandable. Yeah, so and the idea here is that Barani, just because. So there is no special idea why this function should be used, because you can use it, yeah, and you can use it in a project. This is the hyperparameter search that you do, and you just need some special function to encode an embedding, and you can do it in multiple ways, generally speaking. So you can even build neural networks that with additional layers that computes these embeddings, and with the weighting matrix there. For instance, when we're dealing with knowledge graphs, that's exactly what we're doing. But the simplest thing that we can imagine is just to make the ANR multiplication function. Yeah. And yeah, great. So we have a list of train edge embeddings and the correct labels if they exist or not. So one's used for real edge and zero's used for false edge. And of course, we have the negative sampling here. So we have a list of edges that really exist. We have a list of edges that do not exist, and dealing with link prediction task, creating the negative sampling is a pretty complex and difficult story. So in this case, several very important moments about exactly this workshop. Yeah, so we have removed the edges randomly, which in many cases is not the best strategy, because usually in real life processes, edges are not being added randomly. Yeah, and that's why removing edges randomly is not really realistic. Yeah, we will discuss it in a minute. And the second thing is that we are picking the negative sampling nodes randomly. So it means that we're picking two edges, and if there is no connection between them in the original graph, then we say that this is the negative sampling information. Yeah, and that's it. And generally speaking, this can be improved because for machine learning tasks, it's interesting to highlight that to those nodes are pretty close to each other, but for some circumstances, they are not connected. Yeah, and that gives your classifier pretty valuable information that will be used for further training. Yeah, those samples are much more important than just two random nodes. And just once again, dealing with knowledge graphs, it's a very large area of graph modeling where you have nodes representing some structural facts. For example, Peter went to Mary, yeah, or Peter loves Mary, and you have two nodes and relation between them, yeah, and you can model those kind of relations, predict them, and to do this, you also do negative sampling, and it should be done very carefully. And the same story here. Here we're just picking them randomly, but it's not the best strategy. And just for the simplicity, we're doing it in such way. But if you will try to solve the real life dating or link prediction problem, so try to optimize negative sampling in with some strategy that will highlight the important information for your algorithm. Yeah, but it's very long talk. I'm not sure we do have time for this now. And so given those static embeddings, we are building the classical logistic regression classifier using scikit-learn, and we have a list of removed nodes, the removed edges that we want to reconstruct, and we're checking if this removed edge will be reconstructed or not. And doing this, we're getting the average precision and Hawk scores, yeah, and the results for node2vec are pretty high. In fact, this means, first of all, that the entire network that we're analyzing is pretty simple, and all algorithms here are showing good results. Yeah, so generally the network is very dense, and everyone is connected to almost everyone. So several edges give you a pretty high score. But so let's highlight that on the test data set, we have the precision score equal to 0.97. Yeah. If we flash back to the link prediction with the traditional algorithms, the same problem here. This is really my first time when I see edges separated. Maybe it's because we have changed the size of the window. Something like this has happened because it's rendering given some coefficients and coordinates, wherever. And I guess I have a cheat strategy because I have my own Jupyter server here, and everything should work here. Most likely, I even have the storage results here. Let's just jump to them back. And yeah, so we have talked about several traditional strategies, and the first one, let's pick this one, the Jacquard coefficient. Yeah, once again, a reminder is that we have an intersection of common neighbors divided by the union of common neighbors. Yeah, and for this case, without any machine learning, regressions, and supervised information, just looking at the graph without even node embeddings, yeah, we have the average precision score equal to 0.93. And once again, we're not doing any machine learning. We're just saying that if two nodes have many neighbors in common, then most likely they should have an edge. Yeah, and this is our general strategy here. If we try to do the same to implement the same idea with atomic ADAR score that does almost the same, but computes the score with additional normalization coefficient, we get even better results, and our average precision score is 0.95. Yeah, 95 and 4, which is better than this one, but still worse than our node-to-back strategy. Yeah, and finally, the preferential attachment strategy, which is based on another heuristic without any machine learning, once again. So we're saying that the reach should get richer, and if the node has a pretty large number of connections, then new connections should probably happen to this node. Yeah, and in fact, this heuristic works extremely well, especially for dating services. Yeah, so when you have no idea to whom connect this user, just connect it to the most popular. Most likely, he will like it. Yeah, this is general idea here. If you also weighted with the additional page rank information, most likely you will get a very strong baseline, and that's the thing that people are oftenly doing. Yeah, but in this case, we have a pretty poor precision score, which just can be explained by our removal strategy, because we have removed the nodes randomly, and then without any formulation of our removal strategy, just ask the algorithm to add several edges to our original graph, yeah, and to our filtered graph. And if we were removing edges based on the preferential attachment strategy, obviously a preferential attachment would give us the best result. And here, so since our removal strategy differed from the algorithm, so the results are pretty worse. Yeah, in real life tasks like dating, you would probably obtain pretty good results with the preferential attachment strategy. But still, if you are not using machine learning for fine-tuning your practical problem, you get worse results, because all three of those heuristics here showed worse results than just the basic logistic regression based on node-to-back. I need to check if, yeah, I have an SVD computation here. If there are results, we'll just look through them. But if they're not compiled, I guess so you can do it later without me. No, just open it. And yeah, the same boilerplate here with splitting to train and test set. And yeah, we do have the results here. No? No. Yeah. Let's check. I guess that training process is a bit more sophisticated here, because here we have just a small neural network that solves the practical problem. So we have the same edge input, yeah, based on the products of two nodes, but we have a kind of three-layer network with three linear layers, and then several dropouts that computes the final probability to form an edge. And the result. So it's training. Okay, I'll have to scroll it until the end. Sorry for this. and almost done. Yeah. So surprisingly, average procedure here is even worse than in case with the preferential attachment strategy. In fact, it looks like we need to build the plot and see if the model is being overfitted, because it looks like there are a pretty large number of epochs. But generally, so even although the loss is pretty small, our average precision is pretty weak here. Yeah, and generally, this is how things usually happen, because if you look through the paper that I have recommended at the theoretical part of our talk, some algorithms and some factorizations are better for classification tasks and or, for example, community detection, and SVD is extremely good for it. Yeah, and some embeddings suit better for tasks like link prediction, and usually you get pretty good results using the node-to-vec and graph neural networks that we'll talk about at the second part. Yeah, so as the sum up for the first part, you can build or you can make representation learning and build some representations. Okay, it's not learning. You can just construct some representations of your nodes depending on the connectivity information, yeah, about the graph structure. And you can use this information in practical machine learning tasks on graphs. Yeah, for instance, the most typical one and most recognizable is link prediction. Yeah, in this case, we have explored 3 different cases and tried some kind of classical network, no, kind of simple network heuristics based on neighbor information. We have checked the SVD computation on the adjacency matrix and used pretty tough classifier for this. And we have used node-to-vec with a pretty weak classifier based on logistic regression. And our best result was reached with the node-to-vec strategy and so the last one. I guess I'll make a small stop here and ask if there are any questions about the first part, because otherwise we will jump to the second one. Okay, so then let's move to the second part, and our goal is all the same. So we want to build the graph embedding that will fulfill our practical task criteria. So the idea is all the same. We want to generate some vector that represents our node, but we have several additional additions. So first of all, we want to inject additional information about our nodes. For instance, we know that so this node is connected to this one, and we know its gender or its age and some other features that we want to use during the classification. For example, when we are talking about article, you can say that, okay, so this article cites this one, and we also have an abstract that can be described as an embedding or as vector, wherever it is. Yeah, and we want to combine those information sources. The second idea is that we want not just to build static embeddings that know nothing about your practical task, but we want to train our representation in such a way that it can help us for our practical task of the classification. So we want to build such representation that will simplify our final classification problem or wherever problem we're doing. Yeah, so we want to take to simplify the task for the classifier by optimizing the representation of our nodes to make the classifier split it easier. Yeah, here we meet a pretty different approach based on message parsing. Yeah, so the idea here is that our embedding should be pretty focused on the information of the neighbors of the given node. Yeah, for example, the third node, and take into account the features of the nearby nodes in some rational proportion. Yeah, so this is done by some kind of intuitional, just mind model called message parsing, and the idea is that our nodes are kind of sending messages to each other. Yeah, and for instance, if we're looking at the central node, then the nodes that are inside its ego graph are sending some message information about them, and our central node is some kind of the same with the filth hypothesis. Yeah, so the central node can be represented by its neighbors, and if we take into account the information that comes from those neighbors, then we can make a better decision about the central node. Yeah, so we're collecting all those messages from the periphery nodes, and no, it can become larger. Yes, this one is okay. And then change the state and the feature of the third node. So, for example, we have some feature vector that contains 4 components, and now this feature vector is being updated given the information that this node has received from its neighbors. And all neighbors nodes are also updated given the information from their periphery. Yeah, and generally we have 3 large blocks of this framework. Yeah, first of all, we need to decide what is the message. Yeah, what are we going to send to another node? For instance, the simple case here is that we will just give our feature vector. We'll say that, okay, I am female, 40 years old and living in St. Petersburg. Yeah, and this is my feature vector that I'm going to send here. Or I will just send this information kind of normalized with some function or wherever it is. Yeah, the second block here is the aggregation function, because we receive multiple messages, and the key idea of this framework is that our message function should be fully tolerant to the sequence of the messages it receives. So it doesn't matter. I guess I have a nice picture about it. Yeah. It doesn't matter if my message will come the first, the second, or the third. My aggregation function should be permutation invariant. Otherwise, depending on the order of my neighbors, I'll get different results, which is not realistic for social networks. And at previous step, when we were talking about the random walks, we solved this problem just by generating thousands of walks, and our assumption was that in one case this neighbor will interact with the central node, in another case another one will interact with the neighbor node, and just the large distribution of those connections will make this distribution and the sequence of neighbors that interact with the node more or less equal. Yeah, Here, we are not going to make random walks. We're going just to make convolutions aggregating information from neighbors, but our restriction is that our convolution should be tolerant to the number of neighbors and tolerant to their sequence. Yeah, and the classical aggregation functions here are illustrated. For example, you can say that, okay, I want to take the sum of those messages, and message is just the vector that describes the node that we have. Yeah, so vector describing some neighbor. We can just sum them all. We can average them all. And for example, we can pick the strongest one, yeah, the most kind of weighted one. Yeah, so these are different typical message functions. And the third block here is an update. So we have received the message, and now we need to update our central node in such way that it should take the information about those messages. Yeah, so we're computing new embedding using the aggregated information from these messages and using them and the central node embedding, of course. So let's talk about update. And so generally we have our feature vector of the node I at the given k state. Yeah, for example, 4-component vector. And we have these messages received from other nodes. And so using this information with some nonlinear function, we're getting the new state of the function that can be used for further steps of our optimization. And here there is a very large list of possible strategies. For example, you can just ignore the original state and only take into account the information about from neighbors, the messages. Yeah, you can normalize the message in such way that it will not affect your node pretty strongly. Yeah, you can add additional nonlinear functions and weighting matrices that will kind of normalize the importance of different nodes, and so on and so on and so on. And right now there is an enormous list of algorithms that more or less give you an opportunity to compute these update functions. Yeah, I guess one of the most promising one is the graph attention framework, where you have additional information about the attention matrix that shows if the neighbor node is important in terms of if it is influencing the central node in terms of your practical classification problem. Yeah, and you can give different messages different weight based on this attention function. But right now we'll talk about Parani, this is an extremely good question, and generally it depends, because in some algorithms, so the classical trick here, sorry, so the question was, can we choose all nodes to connect it to the central one, or should we make some subsampling? And usually, so there is the additional block here, yeah, about improving scalability. And you can see that node level sampling is one of those tricks. Yeah, so for example, in GraphSage algorithm that is pretty oftenly used as the baseline, by the way, yeah, proposed by Yuri Leskovets, the same as the node to back, also proposed by the same author. Yeah, and here, so this is just the same picture. So this is our ego node, And for each node, we will pick it as a node and look at its neighbors. And this is the neighborhood 1 distance. This is neighborhood 2 distance. Yeah, we have an aggregation, and the aggregation in GraphSage is just the sum. And we're exactly doing the random subsampling of neighbor nodes because we consider that generally we do not need information from all nodes because it would be more expensive for us to compute, but we'll still get pretty good results if we filter some of those nodes. Yeah, and that's exactly what's happening in the GraphSage algorithm, and it speeds up the computation, still giving pretty good results. And in fact, there should be another picture here. No. I guess it's not, it's the different paper, sorry. So generally, I guess the answer is yes, you should subsample them, and subsampling strategy is important because the random one is not the best. And let's go back to the message parsing idea. So yeah, and once again, the message function, the message stores generally 3 elements. Yeah, first of all, you have the source node, hi, you have the target node, j, you have some given step, for example, the first, the second, the third, and so on. And you have some edge information that also can be taken into account because in many cases, for example, once again, in knowledge graphs and chemistry, edges differ, and you need to store some edge vector when you're building the message. Yeah. So several strategies how you can store information about the neighbor. The simplest one is just to copy your message. So you're copying the state, this vector from your source node and sending it to your target node. Yeah. Another strategy is just normalized copy. So you're normalizing it by the number of neighbors of the central node J. Yeah. And the third option here, as I mentioned already, is the attention. So depending on your practical task, you're computing the attention metrics and see if you should take these node information with larger weights rather than from other nodes. Yeah. I guess I should just open the picture because the paper about graph attention networks, because it's there's a very by the way, it's a brilliant graph attention network. There's a pretty nice paper. This is just the page by the author of the graph attention networks, Peter Vedikovich, and so it gives you larger details about this model. Same, so the half of the information here is the same with the paper, but there are some additional pictures, explanations, and so on, and he is updating it from time to time. So I guess it's pretty informative. Yeah, and so the model is described here. You have each one node, and you have some hidden vector here, and at the next step you get h1 prime that stores the information from the node itself and all its neighbors with some averaging strategy. Yeah, and depending on the attention metrics, you will take more or less information from its neighbors and the node itself. Yeah, so this is the general framework here. And yeah, the classical model here, it's another very well-known graph called Cora. Yeah, Cora is just a network for constructed by Andrew McCollum where he stored a pretty large list of papers citing each other. If I'm not wrong, something like 5,000. And he has built the taxonomy of different rubrics, for example, information retrieval, databases, I don't know, natural language processing, and so on and so on. Yeah, and the goal here is to predict what is the category for each paper in his catalog. And the cool story about this data set is that it's really hard to solve this task using only information about the citation graph or only information about the paper abstracts. You also have the textual data there, but if you use only one source of information, you get pretty worse results. Yeah, because abstracts are written by different people and so highlight different aspects of their papers, and really it's hard to say where we should put this article based only on abstract. And the same happens with citation graph, because citation strategies are different. In some cases, you are just citing very important papers in your area. In other case, you're citing most closed papers. And the third case, you're citing, I don't know, your friends, wherever. Yeah, so based on citing information, it's also hard to detect what is the relevant rubric. But if you combine to those strategies, you get a very, very, very nice result. Yeah, and graph and the message parsing framework and graph attention network is just one possible case of this model can deal with it pretty well. So most benchmarks on node classification tasks are reached exactly with GCN or GAT models, wherever it is. Yeah. Let's jump back. So we have discussed the message function, we have discussed the aggregation function and the update one. Yeah, everything is pretty simple. And so the classical approach here, one of the first models proposed is called the GCN, Graph Convolution Network, where you're having just the message function with the ReLU function and weights here. You're using the normalized information given the number of neighbors, and you add all this inside the nonlinearity. Yeah. And GraphSage is a bit different because it doesn't sums everything, it concatenates the messages. So there is a small difference there. And I guess we need to jump to the practical step of this talk because yeah, here it is. Sorry. Our practical task will be about the no. That's wrong. Sorry for this, but there should be a link here. Maybe it's here. I need to drop this because I wasn't going to talk about graph classification. I was going on to talk only about the node classification. So I'll fix this later. And generally, to handle the framework, we will use the DGL, the Deep Graph Library. So originally it was developed as a research project with from 2 universities, or yeah, something like this. But then industrial partners start to contribute inside it. And so generally, if you want to do some kind of strong machine learning on graphs, DGL is your best friend, because it solves almost all possible tasks that you need and automates multiple steps of your research. Yeah, so well, I guess I have just recently updated this picture. I'm not sure if this 1.0 release, but yeah, here it is. Yeah, 1.0, everything is correct here. And so they have added just pre-built functions that help you not only to solve node classification task, but also for edge prediction, just as we have looked 10 minutes ago, the entire graph prediction, graph generation, a very hot topic about the explanation why this answer has happened. Yeah, and general representation learning. It has a pretty large list of pre-built functions that simplify your coding. Just for example, so you can easily access all information about your nodes or about your edges, N data and E data. Yeah, you can quickly add, for example, reverse edges. In many cases, you need symmetrical edges. If you have one edge going from A to B, then you need a reverse edge from B to A. And self-loop, for example, in graph intention network model, you need the self-loop. So everything is pre-built there, and you just write one function and do not spend time. And so some functions that give you information about your graph, and for example, some code that give you an opportunity to make an update, yeah, like message parsing. For example, if you want this update to be an average of all your states for the given node, for the neighbors of the node U, then it looks like update all and just copy the information from X to message. Yeah, and then you need to also make mean just to average it by the number of neighbors, and that's all. It's much easier to do the same rather than to work with PyTorch geometric, because originally the first articles written by researchers were done in pure PyTorch, then PyTorch geometric framework. And I can show you several examples of code where the model is implemented in pure PyTorch geometric code. And I guess it will, so usually it terrifies most of my students, yeah, and DGL is much simpler and quicker. There are several other models that are being developed, for example, Giraffe from DeepMind, yeah, and if you are a fan of Keras, I don't know why, so there is the TensorFlow GNNs, but so generally they're done by pretty good guys, and the frameworks are very promising, but right now the kind of the industrial standard is the DGL framework. And blah, blah, blah. Yeah. So we have the collab about node classification that we will dive into now. And just a small talk before we jump in is about the OGB benchmark. So the idea is pretty simple. The idea is pretty simple. To compare different algorithms, we need more or less equal data sets and equal information that the algorithm can use. And the source of these classical data sets are just the same as, for example, superglue in NLP, yeah, where you have a list of typical problems with typical data sets, and you check if your model solves this problem more or less better. Yeah, and the same happens here. So, in fact, social network analysis, especially the block with machine learning, borrows lots of information from NLP, so here are just several classical tasks: the node property prediction, the link property prediction, the graph property prediction, and the large-scale graph classification. Yeah. So this one is about classifying the nodes, and we will dive into exactly this one prediction. The second one is about the link prediction, and the third one about the graph classification. For instance, if you have some molecular graph, and you need to predict if this graph is toxic or not, if it will cure cancer or not. So you're solving the graph classification problem. And usually graphs are pretty small, but you have an enormous amount of those graphs. And yeah, recently we have done the small research about predicting the toxicity of the chemical combinations that are being exported to Russia. So it has a pretty strong intersection to these data sets, but the chemistry objects are in our data set are different. And so right now we'll solve a more classical and more simpler task, the node property prediction. And our goal is to predict the label of the node, given some information about it. And we will try to do it based on the ANR-Hive dataset, which is just another citation dataset where you have 40 subject areas from ANR-Hive, mostly about computer science, obviously, yeah. And so you need to classify those papers given the network information about them. And there is the leaderboard, where there is a pretty large list of algorithms, and some of them have arrived almost like several months ago, yeah, that show you more or less good results. But so our goal here is just to build the classical GCN model, singular convolutional network. And most likely we will be somewhere at the end of this table. I guess so. This is our goal. Yeah, maybe a month or two, and we will not see this result because new algorithms arrive every month. Yeah, and generally you can see that what are the column names here? The test accuracy for this classification problem. So predicting one among 40 rubrics is 0.75 here, and this is our goal for this workshop. Yeah, and state-of-the-art algorithms solve this problem with something like 0.87, but there are lots of different heuristics, just borrowings from different models, and pretty complex tricks inside them. Yeah, so we're not going to deal with this model, for example. In fact, I haven't even seen it before because I don't know what is the idea behind it. It's pretty. In fact, not very contemporary. And oh, sorry, we're in the wrong domain because we were talking about ANR-Hive and then jumped to another data set. Yeah, this one, and arrived a month ago, and I still don't know what's happening there. Just I guess we need just to read the paper. And the good thing is that we also have a more or less working code here that you can use just to reproduce these results and check what's happening. Yeah. I want to change my screen because I have this because I have this notebook written at my another PC, and I guess this should be it. Let's stop share here. Yeah, it's working. Sorry. I guess the sound is okay. And so let's start walking through this notebook. Standard imports that we have, math, numpy, SciPy, torch, and matplotlib for visualizations, nothing to look at. The cozy trick about DGL is that most likely you would like to run it using GPU because it will speed up your entire computation. If you're going to do it, you need to find your installed CUDA version that should match with your computation device. So you need to spend some time just finding out what is your current GPU, what is your CUDA, and then install the proper DGL version of the library. Yeah, and it usually takes some time. So this is just the syntax that you need to run, and this should highlight your current CUDA version if it is installed. Yeah. Then this is the small supplementary function that just builds losses. Another supplementary function that makes one step of the training processes. So just nothing to look at here. Yeah. Here we are just checking if we have predicted our label good or bad. And if it matches, then everything is good. If it doesn't, then you have a problem. The entire training step that just combines all this information to each other, where you have, so we're defining the Adam optimizer here, the initial values for accuracy, and just iterating through epochs with printing information for each 50 iterations within one epoch. Yeah, and so if we are not seeing the improvement, then we're having early steps. So if you're familiar with neural network training, everything should be pretty familiar to you. If you're not, then I guess we don't have enough time to explain everything here, because then we need a separate lecture about PyTorch, and it will take, I don't know, something like a day or two to dive you into. Generally, so the thing that we're focused on is that we have some model that will be defined within the DGL framework, and we have a graph that will be downloaded from the Open Graph benchmark. Yeah, we also have information about the features of our nodes that would be used within the message parsing framework, and we have the real labels that we want to reconstruct, and some of them will be masked depending on our step. So for training, we will see we will not see the entire information. So an important thing here is that we are using features from all nodes in our data set, but we're not using the label information from our
data set. Because, for instance, the typical case here is that if all my neighbors are from Moscow, then most likely I'm also from Moscow. And this makes the task pretty simple because usually, if you can find this kind of homogeneity, then everything else is pretty simple. But in most of the practical tasks, you have no idea where these people are coming from. You have the true label about several objects, and 80% of their surroundings is hidden from you because they have hidden the city from their profile. But they have several features. For example, they are members of some Moscow groups, and they have some certain edge and maybe certain words in their lexicon. And using these features, you need to reconstruct the label. So this is the goal. That's why. So usually we have a very, very, very significant part of the labels masked or unknown and not used for any other steps of our classification process. Yeah. So we're checking if the device is available, and if it is, then you can see CUDA here. Otherwise, you'll see CPU. Yeah, obviously. And so these are just imports from DGL, the data set evaluator, and the graph convolution model. So, as I said, since DGL is pretty friendly with OGB, you don't need to spend time reading and importing data sets and formulating them in proper structure. You're just importing the entire information with one syntax line, just get the proper data set. Yeah. This should lead in downloading the necessary information for you. Frankly speaking, I have no idea what is stored here. I guess just some necessary data zipped into GZ archives. Yeah, obviously the CSV with the label index information. Yeah, so looks like the paper categories. This was the state-of-the-art results from the table that we have just looked through, just to check if we will beat them later. Yeah, the split index is just splitting your data set with masking some nodes to test and to validation ones. And finally, so this one just reads the data set that you have from OGB archive and sends it to your CUDA device. And the same thing that you need to do to send it to the CUDA device is the label information that you have. Yeah. Your entire graph, so G is just the typical graph structure. Yeah, so you can, as working with network X, you can get information about your edges, about your nodes, and so on. Yeah, so here we have something like 1 million edges, so it's pretty closely connected. Since we're doing the convolution model, we're exactly doing the things from the presentation, self loops and reverse edges. Yeah, and just because the framework supposes us to have symmetrical information about nodes. After doing this, we have a number of edges. Of course, being more than twice, because most of nodes are not citing each other, so you're doubling it with by adding reverse edges, and you're also adding a dozen of nodes by adding self loops, and this leads to more than twice increasement of the nodes. So here starts the definition of the entire model, where you are building the entire convolution framework. Yeah. So you have the list of convolutions that we were going to have, and so this defines that you have the list of layers here. Yeah, and you're putting the graph convolutional layer that transforms your input features to the hidden dimensional features. For example, your input feature size can be something like 500, and your hidden dimension can be smaller, for example, 100 or even 10. And this is the dimensionality that you further will be working with. So at the first step, it's equal to your input features like texts or text embeddings, wherever it is. Yeah, but later you will work with the hidden representation, and the entire rest of the model is working with hidden features. Yeah, and inside your each layer, so you're adding the batch normalization, just that heals you from the exploding gradients. So after each convolution, you are doing the batch normalization. And inside your hidden layers, the structure is all the same, but you're transforming your convolution not from the input features, but already from hidden features to hidden features. So your dimension is not being changed. And finally, your output layer is one more convolution without any batch norm, where you're transforming your list of input hidden features to the final number of classes, which is 40. Yeah, and that's the general structure of the model. So we're just adding all these layers to our self-convolution layers and writing the forward function just as defined inside the GCN paper. Yeah. So there is the nonlinear value activation function inside our message parsing step. And so no attention, no transformers here, and the small dropout just as one more normalization strategy. And that's all. So the code is really simple and really pretty small. Yeah, and of course, you're not doing the batch norm for the final layer, so that's why it's -1. You have 256 hidden features. We have the 3-layered network, which means that we're taking into account the information from neighbors and neighbors of neighbors, and finally neighbors of neighbors, which is pretty large. The dropout is typical for the neural network models, and number of classes is something like 40, sorry, as I said, and we're sending our model to device. So here we are. Oh, by the way, sorry, 2 layers, because this transforms the input features of nodes to the hidden features, and this is the information from neighbors to neighbors, and this is the information from neighbors to the original dimensionality. So in fact, we're dealing only with one with one neighborhood information. Yeah, and this just highlights the number of the parameters that this entire network has. It's just the sum of the dimensions of all weighting matrices that add some nonlinearity to the stored information. And our model is pretty small. It has something like 100,000 parameters. Yeah, people that are dealing with NLP are just laughing when they see these values, because usually when you are working with, I don't know, just some BERT models, okay, 300 millions, let's go, yeah. And here you have only 100,000, it's pretty small. But we have lots of nodes, and each node should be parsed through this model that, of course, requires some time. So the small doesn't mean that it works blazingly fast, but generally the speed is pretty quick. Yeah, and GCN models and even GAT models are usually working much quicker in comparison to the, for example, node to the models that we have discussed at the previous step. So we have some enormously large number of epochs, but we have early stopping, so this kept us from doing 100 more epochs. And the loss that we have dealing with the prediction of the label is shown at the picture here, which leads to, so you can obviously see that after the 100 epoch, everything is pretty stable, and we're kind of working with the plateau. Yeah. Plus, we start kind of improving our results for the training data set, and this looks like a pretty strong overfitting. Yeah. So these are just some general ideas. I guess this is the yeah. If you have a look at several papers, then you can see that one of the possible strategies for the improvement is changing your loss functions and adding the logarithmic function to the cross-entropy loss, which leads to a more kind of smooth loss function at near zero, and finally to better classification results. And this is just a small improvement implemented here. If you're interested, just write me a message. I'll send you the paper that where this hint is borrowed. But generally, there is a pretty large list of hints that give you some improvement, and so a good paper is the combination of those hints. Yeah, and so this is the test that shows that the result has slightly should slightly improve. Let's see what's happening here. So we have the best tests accuracy equal to 0.7171. And here is 7227. Yeah, it's something like 1% better after dealing with this log year function. Yeah, and the plot is obviously the same, but we have got to the plateau a bit quicker. Yeah, just because we have optimized the loss function. So I guess, so this is another attempt of improvement where you can see that we're continue optimizing even the further epochs and further steps of the training. And the hint here is that we're adding the residual connection to the layers and keep the information from layer to layer. Yeah, and it's just another idea of the model that can work better with the same framing of messages and message parsing. Yeah, we're just playing with this forward function here. And as I see it, from one point, we can see that we have a more longly going improvement. From another point, we can see that this improvement is still weaker than the best result that we have received with the logia function. So even though it improves even at the step 150, so the overall result is worse. So this doesn't help are talking about this research. Yeah, and most likely, so these are the papers that I was highlighting about, talking about different hints that you can try while dealing with network approaches. And the overall result here is something like 0.72. If we jump to the GB framework, yeah. Okay, so leaderboards, we're doing the node property and the archive, and the GCM, the classical GCM here was, so we're here, oh, here it is, and so it was 0.71, and it's something very close that we have received from the very beginning. And this improvement of the loss function led to the result equal to 72.4, which is 72.4, which is, yeah, I guess 72.6, 72, yeah, which is at the 46th place of the leaderboard. Yeah, so which means that generally we have jumped from the 57 to the 46th place with a very simple change here, and that's pretty good from our overall result. And most likely your results with SVD and with for example, node2vec would be much more worse. So here is node2vec result. It's 0. Okay, not much worse, but you have more control parameters where you can change something here. Yeah, so this model can be easily improved, and within node2vec you're more limited with the options of the representation learning based on the strategy of random walking. Yeah, so most likely this result cannot be strongly improved, but this one can. Yeah, so I guess we're done for today in terms of time. Irina, is this true?
Yes. I think that we were supposed to finish at 6:15. So we have 10 minutes if there are some questions.
Okay, so I will just sum up with the second part.
Sure.
Here we have not only trained the representation learning step, where we are getting some vectors that describe our nodes, but we have also optimized this representation for our final classification goal. And we have also injected the information about the additional features that come with our articles in such a way that the classification works better. So this is one of the simplest and the dummiest models ever. And just join us to dive into more complex models like GOT and like some hints that lead to better results. This is some motivation spoiler, and apply networks to your real practical tasks, because as I said at the very beginning, it doesn't matter what you're studying. The methods used here are all the same, and they can be utilized for most practical tasks, starting from chemistry and ending with social sciences, and lead to better results in your practical problems. Yeah, so thank you. Barani, generally, yeah. You already had not the hidden but the input features, and in most cases you really have them, because so you know something about your nodes. For instance, their So if we're talking about people, their age, their city, wherever it is, yeah, their biography at least, yeah, or their, you know, the status that they write in social networks. So you have this information. That's the one step. The second hint here is that if you have no information and you're just having the random graph, so you always have the Xavier distribution and just a random initialization. That is the classical pattern here. And the third hint is that you can initialize your initial embeddings with some statistical approach like SVD and then try to fine-tune it. Yeah, so three typical options are used here. Depending on your problem, one can work better or worse. Okay. I really like that at least one person is just diving into everything that I'm telling and asking lots of questions. So that's really great. Okay, I guess then we can stop for today. And Irina, can
Yes,
you?
yes, sure, I'm here. Yes. So if we are done with this session, Ilia, thank you very much. I think that we may, yes, stop here with this session.